Hey everyone, welcome to our November Impact Spotlights event. This is our free virtual monthly event celebrating our Hackster members who are building a better world and the technologies that enable them to do so. This month's theme is connected health. If this is your first time with us, don't worry, you can still watch the recordings from the previous 2 months on the themes of smart ag and smart energy storage. You can find those on our YouTube in their own special little playlist, possibly along with this one, as well as on the Impact Spotlights event page, which you may have used to get here. We'll drop all these links in the chat and in the video description at the end. You'll be able to watch everything recorded and check it all out. So today we're excited to bring you 6 presentations on connected health from our members, brought to you by Nordic Semiconductor. We have a full complement of 6 presentations, so grab a hot drink, settle in, and get ready for some awesome presentations about cool stuff that's going to change the world. Oh, was I not live? I just got a notification. Anyway, there's something weird going on with StreamYard, but hello everyone. In case my intro got cut off there, I will just redo it really quick. So welcome to our November Impact Spotlights event. This is our monthly free virtual event from Hackster.io featuring our illustrious members and the cool stuff that they're building to enable a better world, along with the technologies that they're using to do so. This month's event is sponsored by Nordic Semiconductor. And if this is your first time with us, this is a monthly event, so our previous 2 sessions have been about smart ag and smart energy storage. You can find all those recordings on our YouTube. We have a special little playlist, and it sounds like YouTube was fine, but we had a slight delay on LinkedIn. So anyway, getting notes from my amazing team behind the scenes. Thank you, Jesslyn and Katie, for being on the ball. We'll be responding to your comments, so drop your questions and comments in the chat. Check out the recordings. We're going to drop all the links in the chat at the end, as well as in the video descriptions on all these recordings. We've got 6 presentations for you today, so again, settle in, grab a hot drink, sit down, make yourself comfy, and we're going to have an awesome time. Our first presentation is from Adam Taylor, who is a repeat and frequent Hackster guest, who is going to be sharing a cool build along of this project that he built, which is a smart health and usage monitoring system using FPGAs. It's really cool. It goes beyond your usual talk and into like really the nitty gritty nuts and bolts. So I thought it'd be a good one to kick off with. All right, let's hit it.
Hello, I'm Adam Taylor. I'm going to talk to you about my Hackster project today, which is based around creating a health and usage monitoring system with a FPGA and using a RISC-V microprocessor inside it. What we're actually going to create is this here, which is the Digilant Spartan S7 board. There are 2 PMODs on these. These allow us to monitor the environment that we're in. And we have, of course, the FPGA in the middle. And throughout this application, what we're going to talk about and we're going to create is we're going to create the actual application that sits in the FPGA. We're going to create a RISC-V microprocessor that's running in that. And then we're going to write some software that runs on the RISC-V. And we're going to write some Python that runs on our PC to see and log the data that's coming out of it. The reason why we created this project actually is quite interesting. And that's because for a lot of applications, we want to be able to monitor things such as acceleration in all 3 directions, temperature, humidity. And that's really important for a lot of applications because if you can understand the dynamic forces and environmental forces that equipment's been subjected to, you can work out how its lifetime is going to be, how its reliability is going to be, and generally you can get a much better picture of its failure rate or its acceptability for the application you have. So we find these health and usage systems in a range of applications, from aircraft to vehicles to even space systems as well. So let's take a look. Let's dive in and spend a couple of minutes and take a look at the design. We're gonna split this across a couple of applications. We're going to take a look at the project in Vivado, which is where we've created the application, and we've created the hardware element that goes into the FPGA. Then we'll take a look at Vitis, where we've written the software that's in there, and then we'll quickly wrap up with a little bit of a look at the overall application running and using the Python to grab that data. So as I said, when we wanted to start out creating this application, we need to create an FPGA design. And that is the design that is programmed into the FPGA. Until we do that, it's just a configuration of an array of configurable logic blocks, block RAMs, memories, DSP elements, and we need to harness that and focus that into something functional. So because we're working with an AMD Spartan 7 FPGA, we need to use the AMD Vivado Design Suite to do this. And one of the nice things about the Vivado Design Suite is that we can use the IP integrator to actually create our design. So this design you can see here, this graphical design over on taking up the majority of the display, is actually the FPGA design. So I've not written any VHDL or Verilog to create this one. All we've done is pull together existing elements from the Vivado IP library. So obviously the main thing in the middle here that we can see is we have a RISC-V microprocessor. This is the Microblaze 5, the AMD new processor. And being a soft-core processor, so that's a processor that's implemented in the logic cells and logic resources that are available in the FPGA. This is actually really configurable. So we can see that we can change the configuration of the processor. We can change its optimization, whether we want this to be designed for fitting in a small FPGA or designed for performance, and that will make a difference as to how much logic and how many processing stages are included. As we go through this, we can take a look at the actual optimizations that we want to apply to the RISC-V processor. Do we want to enable code compression, for example? Now, because I want my example to run from the block RAM memory that's available in the FPGA, and this is a relatively small FPGA, then yes, I've enabled code compression on this. But I've not used too many of the other options in this because actually this is a relatively simple application that we're going to be doing. I've enabled the AXI, which is the exceptions for the AXI, and I'm also going to enable the AXI interfaces that allow us to talk and communicate with the external world. So if you're not familiar with what AXI is, it stands for the ARM Extensible Interface, and it is a memory mapped read and write channel to transfer data efficiently within the FPGA. So we're going to do this, and that's going to allow our processor to be able to connect to our peripherals in the FPGA itself, in the fabric logic itself. So within the logic itself, within the fabric, we've put in an IP core for a PMOD navigator. So this gives us the XYZ parameters. We've put in the PMOD hygro, so this gives us the temperature and the humidity. Because I want to communicate with the external world, we've also had to define a UART, so a simple serial UART interface. And then we have some simple GPIO just to test with some LEDs and allow some correction of that. Wrapping up the rest of the system, we have an AXI crossbar to allow the interconnect from the processor to the peripherals. We have the local memory, so this is where our program is going to execute from. And then we have the basics that we need to be able to connect over JTAG and download and debug our application. And the remainder of the logic around here, the clock wizard, the processor reset block, is designed to generate the clocks that are needed for our application. In this case, we're just working from a 100 megahertz clock. And we've also connected in, although I don't use them actually in the application, I connected in the AXI interrupt controller such that we can have an interrupt-driven system. Once we've got this, what we need to do is we need to compile this so it goes through synthesis, place and route, and generate a bit stream, which we can see. Once we have that bit stream, as we can see here, the bit stream is written completely, and we can see then the utilization of the FPGA. So we can see how much of the logic resources of the FPGA this design is taking, and it takes about 12% overall of the logic, which is not too bad. Having this now, we're then able to take through and recreate or even start rewriting our software to run on that embedded RISC processor. So let's take a look. Let's take a look at that. To do this, we use a program called Vitus. And Vitus has a simple concept. It takes the bit stream that we've created in Vivado, along with some additional information such as the sensors, the software drivers that are used, the configuration of the Microblaze, and the address space as well of the peripherals. And then that allows us to create two things within Vitus. The first thing it allows us to create is our application, but But to run the application, we really need a board support package, or what is in Vitis is called a platform. So we get a platform from the bitstream. So we can take our bitstream, we can pull it into Vitis, and that will create a configuration platform for us that has everything we need in the design. So we can see under the microblaze, we can see the standalone, because we're working with a standalone microblaze. We can see all of the things that we need, such as the board support package, to be able to work with this. So here's where we can change the drivers, the peripherals, and anything like that. And this should all reflect through from our hardware design that we've just seen in Vivado. Once we've got that, obviously the next thing to do is to write our application software. So we've written our application software and we've tried to make it scalable. So I've created a simple project. And in this simple project, the first thing we do is we initialize the PMODs. We say that we're going to start command parsing, and then we call this function here called CLI command parser. Now this, you'll see this CLI actually in the code's available in the project. This is something that we've been using more and more in our projects because it's a command line interpreter. So that allows us to receive data over from the UART. Over the serial port using the UART, and then we parse that to do it. So we have simple commands such as read the accelerometer in the X, the Y, the Z, and then we will process that data and send that data back. We also have simple read and write commands, which will allow you to read and write any location in the memory stream. So by doing this, what this means is that our software application that sits and runs on our host PC that's running under Python can then access and control the software any way that we want and read and write with the sensors. So if we open up our application in our Python application, what we'll see is we have a standard Python application that connects over the serial port. We have a function that sends down the command to the user, so the command that we want, whether it be read the accelerometer. And once we've done that, we get the data back, and I want to plot the data on a graph, as you'll see in a minute. So that's what we do there. In the main function, obviously, we basically set up the configuration, initialize the serial port, set up our graph, and then we connect to that serial port and run through. What we see at the end of this is we see a plot, as you can see here, with the real-time data coming up of it from the board. And as we pick the board up and move the board about, what we should see, hopefully, as this updates, is you can see the data is being updated. The real-time plot is being updated, and we can see the changes that are going to it. So we could be logging this and seeing where it goes. So this really is a quick introduction to our project. I hope you've liked it. It's relatively simple to do. You don't need to be an FPGA expert to do this. The instructions are fully in our Hackster project. All you've got to do is just walk through the instructions and follow through the instructions, and yeah, enjoy and have fun.
Awesome. I love that, the way that he really encapsulates the whole little process in that presentation. So our next one is from Tyler, aka Donuts or Else, who has created a smart hiking stick for the visually impaired. What I love about this one is that it's actually useful for everyone. And also, even if you're not visually impaired, it has some extra bells and whistles that could be useful if, for example, you get caught out hiking in the dark, which I will not say has never happened to me. Let's jump in.
So this is for the November 21st Impact Spotlights, and I'll be going over a smart hiking stick I put together. So I'm going to be mostly using this as a point of reference, but conveniently, I have a full project write-up to go through. So first thing was about me. So I like to invent stuff in general. I like to make it purposeful, usually funny. I post everything to YouTube and the relevant stuff to Hackster, but I make things like an interactive mural for my kid. One Halloween, I set it up so that when we watch scary movies, I was checking in on my wife's Fitbit to measure her heart rate and made scary stuff happen in the room to make scary movies scarier. So that kind of stuff. That's what I do. But like I said, I usually like making purposeful things, so contests like this, where it, actually helps people out, is appealing. So the project is a smart hiking stick for the visually impaired, but the idea is that it's so useful that anyone would want to use it, including me. But a lot of the features are specifically geared toward the visually impaired. So it has a ton of features. The first one for the visually impaired is it has a couple ultrasonic sensors. They both face forward, but one faces slightly up and one faces slightly down. And they play tones based on how far away things are. And the tones are in different ranges so that when you learn the different tones, you can actually just know where an obstacle is by learning the tones. Obviously, from the thumbnail, it checks weather, and one of the things it does is warns you if bad weather's coming, but you can just ask it what the weather is and stuff. It accepts voice commands and has text-to-speech, so you can just kind of tell it what you want it to do. I'll show you all the different commands I set up in just a second. But one of the other main aspects of this that motivated the project to begin with was I like the idea of hiking the AT, and when you do a long through hike, you have to coordinate food drop-offs. So instead of doing that kind of thing while you're out and about, it would have geofences set up so that when you make it to certain locations, it automatically notifies the person that's supposed to bring you food, and so it just coordinates all that for you. So I included that, but I also leveraged that same idea to make it so that the visually impaired can have a nice safe walk. So when you leave the house, I guess we'll get to this in a second. I have an animation showing how it works, so we'll get to that in a second. Bill of materials. So the main things are the Unihiker is the brain of the operation. It's the little computer we're using. I only used the Note Carrier F, but I set it up so like you can use either. So I listed both because I showed how to use this, but I used this. So the Blues setup does include the ability to get GPS, but some of the features use GPS without using Blues. So we also have this, and a lot of the features benefit from GPS. So made sense to really go all in on it. And yeah, the ultrasonic sensors. And so design and construction. Basically, so I put together all the electronics first and tried to figure out, okay, where does everything fit? What'll make it look best? That kind of thing. So obviously there's a spot for the Unihiker. It's blocked from rain. I put a little bulge here in the stick. There's a spot for the speaker so that we can have our text-to-speech. You'll notice at the bottom it's wrapped with an LED strip, and a lot of the electronics sit within the stick. So this is all 3D printed, and obviously if you're using it to hike, you need to print with a filament other than like PLA. This is a prototype, so I did use PLA, so this would all kinds of melt, but other better plastics would do the job just fine. So I actually modeled the stick in a program called Medium in virtual reality, and then got into Blender to adjust it. And I used a bunch of pre-built models to just make sure it looked nicer because I'm really bad at 3D modeling, but it felt necessary to do the 3D modeling so that it would actually be able to be customizable to what we need. So I guess for the specific aspects of the code, let's just reference it with the different functions. So set home is mostly used for the walks so that there's a geofence around your house so that it knows when you leave. But you can also ask it like, how far am I from home? So, you know, that kind of thing, helpful there. You can request help. It's sent out via Blues, and someone set up to receive the alerts. You can start a walk manually. You can ask it all sorts of stuff about the weather. Obviously, not everyone needs the distance sensor, so I made it so you can disable it. And this also does have fall detection, which it's been a minute now, but I think it was a built-in accelerometer it had that runs that. So obviously, if they fall, then, you know, sends an alert as well. Or first it asks if they're okay, then it waits a minute, and if we haven't gotten a response, then we send an alert. And if we get a response, it's either to send an alert or they're saying they're fine. The code is complicated. This project took a lot to put together. And since so much is going on, I guess this is the version before I cleaned up a bunch of stuff, so forgive all the comments. But so I had to do a bunch of multi-threading, which ended up causing some issues, but obviously through mostly trial and error, got that to work. Oh, you can also send a message. I forgot about that. So it asks you what your message is. So you say send a message, it asks you what your message is, it listens for it, then you confirm and send it, and it sends over blues. So that's another nice fancy little feature. So I also made it so that it listens for a bunch of different varieties of commands, different ways you could say it. So it'd be enable distance sensor or enable ultrasonic sensor, stuff like that. But one of the other things I added was, so for instance, if they fall or they exceed the expected walk duration, we ask if they're okay, yes or no, but especially if they're hurt, they're not necessarily going to just say no. They might say, I fell or I'm not okay or whatever. So we listen for either positive or negative responses and then process it from there. The weather ended up being surprisingly tricky, but my favorite bug, it's fun to have a favorite bug, but here we are, was the temperature was coming in Kelvin, and I didn't realize that. I don't know why it would default to that, but here we are. So it just made it sound like we were all going to melt and die at any moment. So that amused me. So here's a quick animation on the walk safety idea. If it passes the expected walk time, but they're fine, they can say they're fine. And if not, then it sends an alert. And otherwise, when they get back home, we've got the geofences set up so it automatically finishes the walk. Oh yeah, so one of the main things I knew was going to be necessary was solar. So I actually started off with a much, much more intricate solar setup. And then I just found this power bank that just had it built in. Obviously, we're going to use that instead. It's so much easier, and instead of doing the needlessly complicated setup, I just modeled in a spot for the power bank to sit up front and center. You know, obviously that works great. Now it can catch sunlight. So relevantly, for next steps, one thing that would be good would be to have a clear case for this around it so that it can't get wet. The version of the model that I posted here is better than the one that I used in the video, but I would still want to further iterate this, probably make it a lot more narrow. It actually felt fine for me, but I don't know. I definitely would do a bunch of further tweaks to the model. Other than that, I'd probably just want to add features in general. One thing that would be really cool though, so recently I made basically a similar device in terms of it uses the Unihiker and the Blue setup, but it controls my smart home and includes AI control. So similar to what I used here, I could potentially have the smart hiking stick communicate with my smart home, and the smart home could communicate with AI. So I could basically ask the smart hiking stick for any command or any information or whatever, and it just routes through my smart home via Blues and gets whatever information I want via AI. And so just kind of unlock basically any information you want. You wouldn't have to come up with any of the features in advance if AI can just do it for you. So that would be a big enhancement, and I think that's about it. So that's that project. Like I mentioned, my profile is the Donuts Relics on Hackster. It's Donuts Relics on YouTube. And other than that, you could pretty much find me under Donuts Relics as my handle everywhere. So Instructables, Hackaday, DevPost, everywhere. So that's it. That project took me absolutely forever to put together. So hopefully someone out there enjoyed it, and hopefully you enjoyed this shortish presentation. Have a good one.
I definitely enjoyed that one. Okay, so I didn't even realize that it's a smart hiking stick made with Unihiker, which is amazing to start out with. Tyler mentioned the AT, which is the Appalachian Trail. Having friends who have hiked the Pacific Coast Trail, I can say that definitely coordinating food and like care package drops is very important. So lots of those features seem really useful to people. Also, I'm a huge fanatic about solar power. I'll learn more about it, so I'm going to dig into that project soon. Next up, we have a message from our sponsor, Nordic Semiconductor. So the reason that they're sponsoring this is because they have a vested interest in the future of connected health. And so we're going to be running a webinar together, and we have a short message from them about the contents of the webinar and what you can look forward to. Remember to stick around for all the links in the chat at the end of this event, and then also we're going to put it in the video description if you're watching the recording, so just scroll down after you watch the rest of this, because there's more cool stuff coming up. We got 2 more presentations for you. Okay.
At the beginning of the 20th century, the world's population has grown by 410%, and it keeps growing. Not only is the population growing, but we also live longer. This raises some serious questions. Do we have the means to take care of the growing population? Do we have the necessary resources, hospital beds, doctors, and nurses? Can we rely on traditional healthcare solutions? No. We need to look for ways to improve how we approach these challenges. Hackster and Nordic Semiconductor invite you to learn more about how smart technology can improve people's lives and healthcare solutions. In our live webinar, we will talk about how high-performance, low-power wireless technology is changing the way that we live, work, and play. As a world leader in wireless IoT and low-power connectivity, Nordic is uniquely positioned to enable solutions for telehealth, patient monitoring, disease monitoring, and aging independently, among other use cases. Nordic enables highly efficient sensing, processing, and transportation of health data in a secure and private way. Nordic is a world leader in Bluetooth Low Energy, Wi-Fi, and cellular IoT. We also develop the world's smartest power management ICs and cloud services to ensure end-to-end system-level performance in healthcare applications. During our healthcare webinar, I will talk more about use cases, requirements, and solutions where technology can help improve healthcare and people's lives. This will be a live webinar, and you will have the opportunity to ask me questions. Thank you. See you soon.
Awesome. So, heading into our second pair of presentations, we have a blazing fast one from Evan Rust, who is also a frequent Hackster contributor. He makes projects, he writes tutorials, and he also contributes to our Hackster News blog. So you've probably seen articles from him before. He's going to be sharing the open source pulse oximeter that he created for COVID-19. Take it away, Evan.
Hi, for my Hackster Impact Spotlight presentation, I'll be going over my open source pulse oximeter for COVID-19 project, which I published in early 2020. Now first, a little bit about me. So my name is Evan Rust, but you probably know me as Arduino Guy, as I went by that name for several years. I started publishing projects on Hackster when I was 14. I'm currently a software engineer, and leading up to this project, I had experience with several technologies, including low-cost microcontrollers, different sensors, the Arduino platform, and computer-aided design. I came up with the concept for the open source pulse oximeter after hearing from others about medical equipment shortages, as in early 2020, there's a shortage of masks, other types of pulse oximeter sensors, and also ventilators. Now, this project is published in early April, which is right when COVID-19 was ballooning into a global pandemic. And I also wanted to use widely available parts and keep costs low, so anyone can create one. Now, this device would act as a stand-in for other pulse oximeters, since it leverages the same underlying technologies and sensors. Now, in terms of the components for this project, I first chose the Arduino Nano R3, because it leverages the ubiquitous Arduino ecosystem, so code can be ported to other platforms if desired. I'm also using the MAX 30102 pulse oxygen sensor from Maxim Integrated. Now that supports I2C communication and has a high sample rate for quick readings. I also went with a 128 by 64 OLED screen based off of the SSD 1306 driver, and this also has I2C compatibility. Now finally, I put everything inside of a custom designed 3D printed enclosure. Now to start my project, I first looked at other similar products, including other pulse oximeter designs that fit around a person's finger. After doing this, I then created my own in Fusion 360. Each prototype was 3D printed and then validated to ensure there was enough space for internal components while also being comfortable to use. Now, there were a couple of challenges I ran into. The first one being that the Atmega 328P, which is the microcontroller on the Nano R3, only has 2 kilobytes of SRAM. So that meant a lot of additional features on the Max sensor, and the screen had to be cut. Now, another challenge was that getting everything to fit inside of the enclosure was kind of difficult, because there were a lot of components, it was perf board and also hand soldered. Now, one of my main goals throughout the entire process of design and construction was getting consistent, reliable readings. So one thing I ran into was that the hinge mechanism was applying too much pressure at first, so this had to be redesigned. And at the same time, too little pressure would also lead to incorrect values, which meant adding a little notch on the back and then having a rubber band that could fit around the entire thing. So if I had to go back and extend this project, I'd first start by replacing the hand-soldered perf board with a full PCB and a much more compact layout. I would then use a more powerful processor that could take full advantage of the sensor's capabilities, and then add a rechargeable lithium polymer battery for improved portability. So if you would like to see more information about this project, you can visit its link here and also view my profile on Hackster. Thank you.
Hey, Alex. Sorry, you're muted.
Thank you. I thought I was doing pretty okay this time. Thank you, Katie. You're awesome. All right, so thank you to Evan for that presentation. I appreciate how he dived into the 3D modeling enclosure aspect of it. As someone who is very interested in wearables and health technology myself, I've made a few different things, including like a lucid dreaming mask, and I have a tendency to rip them off of my face during sleep. And so the more advances in like comfort and things staying on you but not being uncomfortable, that's all very important to me. Really cool presentation there. So next up, Mitun Das has a Touchless ATM project, also focused around public health. And I think that you'll agree that this presentation is very fun.
Hi, good morning everyone. It's another beautiful day and I hope you are having a good time. First off, thanks to Hackster for inviting me and giving me the opportunity to talk about my project today. My name is Mitun Das. I'm a software engineer. I've been writing code for last 24 years. I'm a maker at heart and inventor when a need arises. I love to participate in hackathon and contests because those help me and motivate me to innovate. Also, I get to learn something new every day. I was fortunate to bag some of the awards along the way, including 2020 US-China Young Maker Grand Prize, where I developed a low-cost contact tracing device. People know me from the past can recognize that device. I named it TraceX. In the same year, I designed and developed another prototype, which is Touchless ATM. It was again to help reduce the spread of COVID-19 virus. So this is the prototype I designed that time. It's a replica of ATM machine. You have the keys and everything. And I'll be talking more about this project, how AR was introduced as part of tapping on the keys. So head over to my desk and I'll be talking more about that project. Alright, so let's rewind back 4 years and imagine you are in Q1 2020. COVID-19 is spreading like anything and everyone is doing their best to prevent the spread of COVID-19 virus. Researchers found that time that the primary reason COVID-19 is spreading is through the contacts, meaning people are touching on the same surface, same objects, and that's how virus is spreading from one person to another. So that during that time, I was thinking how technology or IoT can help prevent the COVID-19 virus, and the idea about touchless ATM came to my mind. There are different ways to solve this. I was also thinking about different technologies because in my mind cost is one big thing or factor. Cost can be in terms of building the software or deploying the hardwares at scale. So I was considering all different things, and couple of alternates I thought about that time is using NFC or near field communication, which is very cheap by the way, and compared to any other solutions with cameras and all those things, right? And also I thought about installing a QR code scanner in each terminal, where you can actually show the QR code, and then instead of you typing on the keypad, the same thing will be done through the software. But the problem which I found that time is not the cost of the hardware, but rather is the deployment cost, basically the scalability issues. So you have to deploy the hardware in each and every terminal, which was kind of not feasible. And also the simplest way, you probably can think that, okay, why you need all these tech things, right? We can just sanitize every time after use. But again, like that was not feasible. That was not feasible that time. That is not feasible today, right? So I thought about using virtual reality. Not virtual reality, it's basically augmented reality, where I can kind of recreate the keypad on your phone virtually, and someone can actually type basically in the air, and it will do exactly the same thing what it's supposed to do when you are actually physically typing on the keys. So let me start from my Hackster page. So if you are curious about knowing more about this particular project or any other project which I developed over the years, head over to my Hackster page, and then you will find all the projects and different information. So now coming back to bill of materials, meaning like what are the different hardwares I have used and different softwares I have used. I started, as I said, my primary motivation was to build something very low cost. So I was thinking about not very expensive hardwares. So I thought using probably very cheap microcontrollers, because if you think from a hardware perspective, all you need is basically turn on some motors, right? So you don't need any high performance hardware to achieve your goal. And for my prototype, I was using 4x4 matrix keypad just to replicate the ATM along with the servo motor. And then on the software side, I was using Unity, and along with Unity, I used Vuforia for the augmented reality aspect of the entire project. And I used Arduino IDE to program the microcontroller, and I used some other software technology, for example MQTT for transmitting the messages from the microcontroller to the app, and vice versa. And of course some of the optional things I used is the 3D printer. As you have seen, that prototype I built, that was built using 3D printer, and of course a couple of jumpers. And now so this is the motivation. I kind of talked about that before, what inspired me to build this project, and all different alternatives I thought about this particular project during that time. So let me, before I move further on the technology side and architecture of the entire project, let me give you a quick demo of that. itself, like bits and pieces of the technology. So here is the high level architecture diagram. If I say that, it's it's probably the simplest diagram you imagine. So what I have is the VR app. That's the software part of the project, which I talked about at the beginning of this video. And what happens, your app is basically communicating to your microcontroller through MQTT. So when you are virtually typing, it's all in the air, all in your augmented reality app. So it's capturing all your keystrokes, virtual keystrokes, and then sending that data back to your microcontroller, which is kind of controlling your ATM machine, for example. And then it validates your keys, and then it let you do what you wanted to do. And in my project, I used Vuforia, and how it works is basically you kind of need to have image on which you are going to project your virtual screen, right? So in my case, I have used this rocks image, and actually it looks like this. So for example, like I printed that on a piece of paper, and then you have to use these to project the virtual screen. And I have another project on Hackster, where I kind of walk through step by step how you can create augmented reality app. So if you're curious about recreating a similar kind of project, I would highly encourage you to check out my other project, which is kind of a tutorial. I can go over to my GitHub repository, and this is the AR ATM project which you need to explore. So I have everything listed here. You can follow along this code base to replicate the project. So if you're curious about what I'm working on these days, you can check out my GitHub profile. You can check out my Hackster to learn more about that.
Awesome. Well, that's 4 out of our 6 presentations so far. I really enjoyed learning about that one, and I also feel like I'm gonna go surfing today. Our secondary sponsor this month is Microchip. So huge shout out to Microchip. These folks are also heavily invested in the future of connected health. So we're also going to be running a webinar with them. Here we have a quick message from them to describe exactly what you can look forward to in that webinar. Again, stick around for links in the chat and or check them out in the video description at the end of the program in our recording. All right, take it away.
Hi, I'm Martin Smith, and I'm the America's Medical and Health Guy for Microchip Technology. I've got a couple of important questions to ask. Why are medical services and devices so important to us and to the world? And why is it so important to continue to advance medical device technology and innovation? Well, Steve Jobs, who was known for, among other things, to be a pretty forward thinker, felt that medical technology would be a critical and necessary area of innovation for the 21st century. Neil Asher, a science fiction writer, wanted to make sure that he could travel to a time that medical technology was good because he didn't relish the idea of dying. Now, that's kind of tongue-in-cheek, but he made a good point. And finally, I want to mention the topic of sustainability. Sustainability is about how we take care of our planet. Good medical and health technology is one of the ways that we take care of everyone. If the people on our planet are healthy, they're more likely to be able to take care of this planet. This is why medical devices are one of the important aspects to the sustainability of the planet. Why do we need new medical device technology? Isn't what we have now pretty helpful? Well, yes it is, but things are changing dramatically. Every human being on the planet needs medical services. Governments, charitable organizations, and businesses are driving the global effort to get more healthcare services. This, of course, is driving up the demand for secure and connected medical devices. As you can see, medical services and devices benefit all of us by lengthening our lives, stopping disease, and helping both our individual and global productivity as well as economic progress. These images are some examples of how telehealth, remote patient monitoring, and connected drug delivery can be so important to rural areas, developing nations, and to almost everyone else. So how do medical device designers meet the needs and requirements for these new medical devices? I've listed some that we found to be important considerations in order to meet these requirements. So one of the ways to start and accelerate your medical device development is by using one or more of Microchip's medical reference designs. Here are some of the medical reference design boards that we offer design files and support for to help you get started in making smart, connected, and secure medical devices. So join us on Thursday, February 13th, 2025, when Hackster and Microchip will get together for a webinar chat on new medical device technology. We'll see you then.
I love the emphasis on hope and health in that one. It really captures sort of the drive behind this, which is really a big part of why we're doing these impact spotlights. We don't want you to see these as like just promotional stuff. It really is motivated by making a better world for all of us. And so our next presentation, our penultimate one, is an exciting one from Ramsey, who's created a wearable device to translate sign language to text and speech. Let's hear it.
Hello everyone, I am Ramsey and I'm happy to be here with you today to present my work and my project in the Impact Spotlight of this month. Okay, so the project is wearable device to translate sign language to text and speech. Alright, about me, so I am an electrical engineer who is currently pursuing a PhD in computer science. More precisely artificial intelligence, and I'm also working as a teaching assistant in University of Burgundy in France. So I remember that when I started this project, I was still a bachelor's student in electrical engineering. So the first phase of the development, it was conducted back then. Then the final version, it was during my master's degree. So regarding my background, since I had the chance to have this knowledge about both of the software and the hardware, really helped me to tackle and create multidisciplinary projects. And one of them, it's this project. So yeah, so the motivation behind this project, it was a long time ago. I remember I was just sitting watching a documentary about deaf muted people, and back then I remember it was just when I started working with Arduino and discovering what is a microprocessor, a microcontroller, what are sensors, etc. And at some point I said, okay, let's discover what I can do with this knowledge, what I can do. I wanted to do something with an impact, something that I can build it from scratch. So it was just a challenge. I wanted to challenge myself to see if I can build something just like this for fun. The main idea, it was for fun. So the main idea here is that we wanted a device that it's wearable, easy to wear, and it can translate sign language. So this is the final version of the device. So it can be easy made at home. So it is homemade. It is a low-cost solution for deaf-muted people, and it's user-friendly with recycled components. So all of those components, or at least most of them, like the jumpers, some of the sensors, especially the hand gesture sensors, are recycled from other or old electronics. Okay. So for the bill of materials, you don't have necessarily to use those materials. You can use some others, but from my side, those components are available on the market, so you can really get use of them, and it's not that expensive. It's really cheap. So for the main component, the microcontroller, here we're using an Arduino Nano, but you can use any other Arduino or a Raspberry Pi. We are also using a gyroscope and accelerometer module to capture the hand gestures. And we are using a Bluetooth module, an HT05, jumpers, battery, and joystick. And regarding the joystick in here, it can be easily replaced with flex sensors. So they are both doing the same thing. It's just a variable resistance. So once you vary the resistance, you vary the voltage, and you can read it in analog to digital converter. So it's as easy as that. So now let's go through the design and construction. So the projects and the design went through multiple phases or multiple parts. So each one was an upgrade compared to its predecessors. So the first version in here, the first model, it consisted of a homemade flex sensor, an SD card to save voice recording, and a sound output. So we can see it from here. So number one here is a homemade flex sensor. I remember that back then I hadn't enough money to buy flex sensors online. I remember it was $10 for each one, or I don't really remember the price, but it was expensive for me back then. So I had to made it at home using just aluminum foil and some conductors in between. So flex sensors, it's just a variable resistance. Whenever you bend your finger, you're changing the resistance inside. So also I use an SD card to record the voice. It was just pre-recorded voice of mine and a sound output. So it's highlighted here in 3. So this output can be just plugged into a 3.5 millimeter jack, and you plug it into your stereo speaker, and you will see the voice. So this is the schematic that we can see in here. So these are the flex sensors in here, and here it's a voltage divider, to read a voltage. Whenever the resistance will change, the voltage will change as well. And the SD card and the gyroscope module are both connected to the Arduino. So let's see the first implementation in here.
English or 2 for French or 3 for Arabic.
English.
Speed 1, 1, up, down, right. 1, 2, 3.
French.
4, keys. Say,
Alright, that was for the first model or the first implementation. So we can see that it's really sensitive to the movement. So sometimes it outputs the wrong instruction or the wrong sign. That's because the homemade flex sensors, they were so sensitive to temperature and humidity. So whenever you use the device, you have to adjust the thresholds. So that's why I moved forward for second implementation.
English or 2 for French or 3 for Arabic.
So let's see the second model in here. So instead of homemade flex sensors, I used the recyclable joysticks. So with those joysticks, they were recycled from PlayStation controller. And I just kept the SD card for the voice recording, the sound output also, and I added an extra text data with Bluetooth. So this is the second version. We can see that we are still having here the SD card and the sound output. So let's move to the final version, where we just get rid of all of this stuff and just replaced everything with a smartphone. So this is the last version in here. So we can see that we removed the sound output, and we use the smartphone to show the sound, plays the sound, and also shows the text. So let's get a look.
Hello. 1, 2, 3, 4. All right. Up. My name is Ramsey. Goodbye.
All right, that was it for this implementation, and that was the last time actually I worked in that project. Currently, I'm busy with other projects, but I will just leave the floor to you guys. So if anyone is interested in this project, you can make it even better. So one suggestion that I have for you, if you want to modify it or work in it, is instead of hard coding every sign and its translation, you can just use machine learning to do this stuff for you. So you just need to record your data, label it, and you need to use appropriate component. Like you can use Arduino BLE and TinyML to work in that. If you either want to build a regression model or any other type of AI or ML models in there. All right, thank you so much, guys. It was a pleasure presenting here today. So you can scan this QR code to get the project page in Hackster, and you can see my profile. And if you really need any information regarding the project, you can contact me on X or LinkedIn. So preferably LinkedIn, because I'm usually available there. So thank you so much, and goodbye.
Yeah, I really like how Ramsey addressed multiple different types of accessibility, including impairments and affordability and your language access, as well as, of course, sustainability with the recycled joysticks and also those DIY flex sensors, which is brilliant. Our final presentation here is from Naveen Kumar, who is going to present his device for snoring detection using the sentient neural decision processor. Take it away.
Thanks, Hackster, for inviting me in this talk. Today, I'm going to share one of my projects, snoring detection with sentient neural decision processor. Hello, everyone. I'm Naveen Kumar. I studied information technology, computer science, and bioinformatics. Currently, I'm working as a researcher at RIKEN in Japan, and I have been mostly doing microbial genome sequencing data analysis and mouse behavior analysis. I'm one of the active project contributors at Hackster.io, and I have won more than 10 awards in various contests. Also, I'm an AGI and robotics enthusiast. So the word snore was first used by William Shakespeare in his play, The Tempest. Before this, people called snores snorts. It is estimated that more than half of men and over 40% of women in the United States snore, and up to 27% of children. While snoring can be a harmless occasional occurrence, but it can be also an indicator of a serious disorder. Snoring is caused by vibration of tissues near the airway that flutter and produce noise as we breathe. Snoring often indicates obstructive sleep apnea, a breathing disorder that causes repeated lapses in breath due to a blocked or collapsed airway during sleep. Despite being unaware of their snoring, many people suffer from sleep apnea, leading to underdiagnosis. For proof of concept, I have developed a non-invasive, low-powered edge device that monitors snoring and moderately interrupts the user through a haptic feedback mechanism. This device is not intended to be used for medical purposes, though. So I have used the Arduino Nicla voice that has a ARM Cortex M0 core and also a sentient NDP 120 neural decision processor. That is kind of a neural network accelerator or engine, but very low powered. And also it has a PDM microphone, which we will be using in this project. The second item is the Adafruit DRV 265L haptic motor controller and a vibrating mini motor disc. And for training, testing, and deploying the ML model, we are using the Edge Impulse Studio. So this is the picture of the hardware assembly. So the haptic motor driver is connected to the Arduino Nicla voice using an SLO connector. So this SLO connector is Arduino specific, and it's kind of 5 pins connector. But the Arduino Nicla voice does not provide power from this connector. So we are using one of the headers, VIN pin, to provide the power to the controller. And you can see the schematics in the image. So first thing is we have to do the data collection for the machine learning model training. So we downloaded publicly available datasets of snoring and non-snoring sounds. These datasets were converted to a single channel with a 16 kilohertz sampling rate and uploaded to the Edge Impulse Studio. And then we have to do an impulse design. So impulse is actually a set of blocks for building a machine learning model in the Edge Impulse Studio. So first block is actually the pre-processing block. So we choose the audio sentient block for the pre-processing of the audio signal data. And another block we added for the classification of the data. So we choose a default window size of 968 millisecond as required by the neural decision processor with an increase of 32 millisecond. So this way we can have actually two complete frames within 1 second of sample. And then we have to extract the features from the data. So for that, we will be using the processing block that computes log male filter bank energy features from an audio signal. So the log male filter bank energy is the logarithmic of the energy output from a series of triangular filters applied to the power spectrum of a signal, spaced accordingly to the male scale. So actually they do something complicated. So if you want to know a little bit more about this, so you can find many resources online, but basically it does some fast Fourier transform also. And here we have to set some parameter for the log male filtering energy features. So I have chosen the default parameter from the Edge Impulse Studio. And actually it generates a spectrogram after the data processing. You can see the spectrogram in this image. And then we have to do the model training. So we conducted experiments to establish the model architecture using a two-dimensional CNN, which is illustrated here. And after training is completed, so we obtained the accuracy of 99.4%, which is pretty good. And you can also see the separation of the noise and the snoring sound is quite good in this visualization. And we have to do the model deployment on the device. So for that, actually, we need to configure the deployment. So since we will be deploying the firmware on Arduino NicoleOS, and so we have chosen the sentient NDP 120 library. And also we need to configure the posterior parameters. So the posterior parameter actually defines the threshold at which a model activates for words or other audible events, in our case, snoring sound. And before flashing the firmware to the device, we need to customize the firmware code for our application. So detail can be found on the project link, which I am going to share in the next slide. So before that, actually, we will watch an inferencing demo. So to detect a snoring event, the application maintains a circular buffer of last 10 inferencing results. And if 3 snoring events are detected, the haptic feedback motor will vibrate for a few seconds. So you can watch the video. So during the demo, the motor vibration appears to be moderate, but the user can still feel the vibration while using the pillow. So the next future steps would be implement a feature for sleep mode to reduce power consumption, enhance the design for a more compact form factor, and create a 3D case that can house both the hardware and the battery safely. And here's the link for the project page and my Hackster profile. And also you can follow me on my X handle or connect to my LinkedIn profile. And also I have provided the QR codes for the project page and the Hackster profile. So thank you for your attention.
All right, that brings us to the end of our presentations. Thanks to all of our presenters who shared their projects today, and thank you for joining us. We really love putting these on, and I hope that you enjoy them too. I'm going to pull up our main event page here right now, and my colleagues are going to drop all the links in the chat, including those webinars from Nordic Semiconductor and Microchip, and also our event page, and then all the projects that we saw today. And I'll also drop those in the video description after the fact. So let's have a look. Of course, you can go to events.hackster.io/impact spotlights. You'll find a description of the event, and the key part up here is subscribe to announcements. Be sure to follow that for email announcements, and also go follow us on LinkedIn and YouTube to make sure that you don't miss a thing. Our next event is going to be in January, but we have plenty to keep you occupied throughout December. For about the next like 10 days or so, my lips are sealed. But I can promise you we've got some really cool stuff. You're not going to be bored. So keep your eyes and ears open for cool stuff around that. You can check out our previous Spotlights recordings, and this is where you'll be able to find information on our January event once it is set up. And let's take a quick tour through some of our projects. We've also got the previous recordings up on YouTube, so go check those out. I'd like to quickly appreciate the variety of hardware that we saw today. We saw a digital and ARDI board with an AMD FPGA. We saw the DF Robot Unihiker, a couple of Arduino Nanos, Node MCU with ESP8266, and an Arduino Nikla voice. We've also seen augmented reality, a VR-designed enclosure, a neural decision processor, voice control and audio processing, ultrasonic sensors, oxygen sensors, haptic motors, and more. So much cool stuff on here, and so much of it with attention to sustainability, to affordability, to everything that makes these things accessible to people around the globe, and really inspiring solutions for tomorrow. So back to our event page. Again, be sure to subscribe to email announcements. Just hit the coral colored button in the top right there if you haven't already. Make sure you don't miss a thing. As I mentioned before, plenty of interesting stuff coming up in December, so stay tuned for that. You don't have to wait till January for more cool hacks. Thanks to our backstage staff, we've got Jesselyn and Katie rocking the world, keeping everything running and dropping these links for you. I'm going to be putting up the recording on our YouTube and also on the Hackster front page. Just go to Hackster.io. You can see all the cool videos we got there. Yeah, thank you again for joining us, and as always, hack on.